Hello. In this video, I'm going to explain the limit, the definition of the limit. And I'm going to take an intuitive approach that I believe you'll understand. Okay. Now this is the definition of the limit here. And there's a lot going on here, and we're going to do it piece by piece. We're going to start with the most basic idea and work up. And until we explain the whole definition. We're going to start with this piece here. X converges to A. Okay? Now, to understand limit, we need to first understand convergence. And convergence uses the symbol X in a way that may be new and unfamiliar to you. Now, any math student has seen X used to represent a single number, as in X plus 3 equals 8. And we figure out what X is. Or sometimes X can represent more than one number. For instance, in this equation, we find roots and X will be 1 or negative 1. And sometimes X, the symbol X, is used to represent any number. For instance, when we talk about the commutative law of addition, we write something like this. X plus Y equals Y plus X. And we mean for any two numbers, X and Y, you can reverse the order and you get the same result. But when we talk about convergence, we should think of X, or at least it can be helpful to think of X as a changing, moving quantity. And that's a new idea for a lot of people. So for instance, let's imagine X is a car, and X is sitting at 0, and it goes to 0.9. And then from 0.9, it goes to 0.99. And then it travels to 0.999, and then it travels to 0.9999, and it keeps doing this kind of thing forever. Now we can ask some questions. We can say, what number is X approaching? We can say, what number is X getting closer to? And we can say, what number is X converging to? Now these questions all mean the same thing, so they all have the same answer. In the example you just saw a minute ago, X is approaching the number 1, X is getting closer and closer to the number 1, or X is converging to the number 1. And the mathematical notation we use for this idea is this. So this means that X is approaching 1, getting closer to 1, it's converging to 1. It means that X eventually gets as close to 1 as we could wish. Now, of course, we need to express the intuitive idea of getting closer and closer mathematically. And we use that using distance. Now, you'll recall that the distance between two numbers is given by the absolute value of their difference. So if we want to know the distance from X to Y, or from Y to X, the order doesn't matter, we just say take the absolute value of X minus Y, or equivalently, we take the absolute value of Y minus X. So here are some examples. The distance from 3 to 5 is the same as the distance from 5 to 3, and it's 2. The distance from 1 to negative 2, we just take one number and we subtract the other. So here we took negative 2, we subtracted 1. Here we took 1 and we subtracted negative 2. Both cases we get 3. And again, the distance from negative 5 to negative 3 is 2. Okay, so converges to 1, which is written as this, means moves closer and closer. It means the distance gets smaller and smaller, which means that the distance, and that's written this way, eventually becomes smaller than any positive number we can name. The distance becomes smaller than 1 over 1,000. It eventually becomes smaller than 1 over 1,000,000. It eventually becomes smaller than 1 over 1,000,000,000, etc. Now, we're going to need a symbol for this idea of any positive number we can name. And we'll use delta. So, not to beat a dead horse, but all these things, X approaches 1, X gets closer and closer to 1, X converges to 1, or this symbol here, mean that this distance gets smaller and smaller and smaller. It eventually gets smaller than any positive number we can name. even 1 over 10 to the 100th power. It eventually gets smaller than that. So that's what this means when we say x converges. Now, of course, 1 isn't important. It could be converging to 2 or 3 or 5 or whatever. But this is the idea. This is what convergence means. If you need to stop and think about what I've said, do that, because we're going to build on the idea of convergence. Here are some examples of convergence, by the way. Suppose x, well, this is the one we used with the car. It goes from 0 to 0.9 to 0.99 to 0.999. Now, it could also be doing this. It could go from 0 to 1.1 and then go to 0.9 and then go to 1.01 and then 0.99 and then 1.001 and then etc. Now, in both of these cases, we would say x is converging to 1. Remember, x, we're thinking of x as a moving quantity, as a changing moving quantity. Now, this example does not converge, by the way. 0, 0.9, 0, 0.99, 0, 0.999. It doesn't converge because it keeps jumping back and forth. It never settles down and just steadily converges to 1. Okay? Now, does x ever reach 1? Well, it doesn't have to. It just has to get closer and closer to 1. That's all we need to be able to write this. In fact, well, what happens if it does reach 1? What about if x goes from 0 to 0.9 to 1, and it just stays there? We have a whole series of 1s. It just goes to 1 and stops. Well, this case isn't interesting or useful for our purposes, so we want to exclude it. Now, how are we going to exclude that case? We're going to do this. We're going to say the distance gets smaller and smaller than any number we can name, but it never becomes 0. Now, that's why we see this in the definition of the limit. And we'll see why this is needed a little later. So, here's the definition of the limit up there, and we've explained what this symbol means. This symbol means x converges to a, which means that the distance gets smaller and smaller. It gets smaller than any positive number we can name. And for purposes of the limit, we also add this, that it never actually reaches a. It always is a little bit away from a, but that distance keeps getting smaller and smaller. So that is what this means. And it means that this is eventually true. This is review. And in limits, we also require that it doesn't actually ever reach a, that the distance never becomes 0, but it just gets smaller and smaller. We should mention another type of convergence, by the way, convergence to infinity. We'd write it like this. And that means that eventually x gets larger and larger. So this is a different kind of convergence, but it's useful to lump both of these ideas under the term convergence. So for instance, we'd say that this, that if x goes to 1 and then 2 and then 3 and then 4 and then 5, and it keeps going like that, we would say it converges to infinity. And of course, x could converge to negative infinity. It could go to -1, -2, -3, and just keep on going. So, to summarize what we've seen about convergence, if x converges to a finite number, that means that the distance between that finite number and x gets smaller and smaller. It eventually gets smaller than any number we can name. It gets smaller than any positive number. It gets smaller than 1 over a million, 1 over a billion, 1 over a trillion, etc. This distance gets smaller and smaller. Now, for limits, we have this added condition. We say it gets closer and closer to a, but never actually reaches a. And that's what this 0 is less than does. It ensures that x never actually equals a, that the distance never becomes 0. So here we're thinking of a moving x that gets closer and closer, like that car, goes to 0.9, 0.99, 0.999, but it never actually equals 1. Now we also have this more general idea of convergence where we say x goes to infinity, which means it gets bigger and bigger. It gets bigger than a million. It gets bigger than a trillion. We also have the idea of x goes to negative infinity, which means x gets smaller than negative million, x gets smaller than negative trillion, etc. Now we're going to add a function to our consideration. Now the first thing to realize is that if you're given the definition of a function and you're given the x, which is the independent variable, those two things determine what the dependent variable f of x does. Those two things determine what the dependent variable converges to, if it does converge. And this is true whether we have x converging to some finite number or x going to infinity or negative infinity. So let's look at an example. For example, let's consider the function f of x equals 1 over x squared. And let's see what happens as x goes to 0. Now, x going to 0 and the function definition determine what happens to the dependent variable f of x. We can see here by some calculations that f of x gets larger and larger. So we can write this as x goes to 0, f of x goes to infinity. And this is an example of why we don't want x to actually equal the number it's converging to. Because here it can't, right? If x was 0, we'd have 1 divided by 0, which we can't do. Here's another example. Let's consider the same function and see what happens as x goes to infinity. As the independent variable x goes to infinity, the dependent variable goes to 0. We can see that here. So we can write this. As x goes to infinity, f of x goes to 0. Now, of course, convergence doesn't need to involve going to infinity. For instance, here's a function 2x plus 1. And we have x going to 1. And I've done it from both sides here. X is going to 1 from the left and from the right. And we can see that in each case, f of x is going to 3. It's getting closer and closer to 3. So we can write this. As x converges to 1, f of x converges to 3. In each case, knowing the function definition and knowing what x converges to will tell you, with a little bit of calculation, what the dependent variable f of x, also known as y, converges to. But you might be wondering, why all this closer and closer business? Why not just calculate? I can put 1 into the function and I get 3. Why not say the limit is 3? Well, for some functions, continuous functions, you can do that. You can just put x into the function, find the value, and say that's the limit. But there are important cases where you can't. We already saw one up here where we can't do that. You can't plug 0 into the function and get the limit. Here's another example. The same function as a minute ago, except we've changed the definition at one point. So it's 2x plus 1, except if x is 1, we say the function has the value of 4. Now, the important, crucial point to understand is that even though g of 1 is 4, the limit of g as x converges to 1 is 3. It is not 4. As x gets closer and closer to 1, g of x gets closer and closer to 3. Now yes, if x equals 1, g of x is 4, but we are specifically excluding that with this 0 is less than here. We're saying we don't want to consider when x equals 1. We just want to consider what happens when x gets close to 1. Okay? So if you have a continuous function, finding the limit is easy. You just plug in the a value and the limit is whatever comes out. Okay? In other words, if x is continuous, the limit of the function as x converges to a is just the function's value at a. But wait a minute, we haven't really explained the limit yet, have we? Well, yeah, we have. This definition means the same thing as this. This definition, or this expression, I should say, not definition. This expression says as x gets closer and closer to 1, the value of the function gets closer and closer to 3. That's what this means. Okay? It means that as the independent variable, in this case x, gets closer and closer to a, the function value gets closer and closer to L. Okay. So now this English phrase, the dependent variable gets f of x gets closer and closer to the number L, we're going to express that mathematically like this. And we need another small number, a symbol for a different small number. We don't use delta because delta applies to the convergence of x. So we use epsilon. Epsilon is the small number that applies to the convergence of f of x. But there's just one point. Maybe you're wondering, why don't we have 0 is less than for the what the function's value, the dependent variable, converges to, right? In the limit definition, we have this for x, but we do not have a 0 is less than for the dependent variable. Well, we don't want that condition for the dependent variable. Why is that? Well, imagine we had the constant function f of x equals 3. Well, as x converges to 1 or any other number, we want to be able to write that f of x converges to 3. But if we had this condition there, we wouldn't be able to write that because it is not true that 3 minus 3 is greater than 0. In other words, this would prevent us from writing this expression, which we want to be able to write. Another explanation, or another way to think of it, is that f of x is the dependent variable. So putting this condition of 0 is less than on the independent variable is sufficient. It automatically takes care of the dependent variable. This is a fine point. You don't have to worry about that too much, probably. Okay, but the important point to make right now is that the limit has been explained. If you understand what we've said, you understand what a limit is. Now, using the limit definition in a proof may involve some cleverness and complicated math, but it doesn't involve any new understanding of what a limit is. If you've understood everything so far, you understand what a limit is. Okay? So this means the same thing as x converges to a, but it never equals a. And if that happens, f of x automatically is forced to converge to L. It means that the independent variable, this expression means that the independent variable getting closer and closer to a forces the dependent variable to get closer and closer to L. Now, it's worthwhile just to look at a simple example of how we actually use the limit definition in practice. Okay, this is a very simple example. Suppose here's our function, which we've seen before, and we want to prove this, and we know it means this. Now, what do we know? We know, because we're given it, that x converges to 1, which means this. And what we need to prove is that this logically implies this. That's what we need to prove. We need to prove that given this is true, that distance between 1 and x gets smaller and smaller. If that is true, we need to prove that this is true. Here's our f of x. And we need to prove that that value gets closer and closer to 3, that the distance gets smaller than any positive epsilon we care to name. That's what we need to prove. Now, how are we going to do that? Well, the only way to link this delta and this epsilon is through the definition, the function definition. Now, we've already seen, this is just a rehash, that the function is continuous. So we could just evaluate f at 1, get 3, and say the limit is 3. But we're using this simple example to illustrate the mechanics of using the function definition to prove the convergence of a function that may not be continuous. So this is a simple example. Okay, to reiterate, we know, because it is given, that x converges to 1. That is, we know that this is true. What we need to prove is that this logically implies that. We need to relate epsilon to delta via the function definition. So let's write what we want to prove. We want to prove this. Now let's expand. Well, we've already added the function's definitions there. Now let's just expand and work with this. This equals this, which equals this. And that implies, this line implies this. All right, we kind of now read off the proof from the bottom to the top. If we set delta equal to epsilon over 2, then we know this is true, and we know this is true, and we know this is true, And we know that's true, and that's what we're trying to prove. So we're done. We have successfully linked epsilon to delta. We've shown that if you give me an epsilon, and we want this to be true for that epsilon you gave me, I just select delta of epsilon divided by 2. Because if I select delta of equal to epsilon divided by 2, that means that this is true, and this is true forces this to be true. And so we've satisfied the requirements of the limit definition. Okay? Here are some calculations which illustrate that if this is true, this is true. So here we're given an epsilon. We set delta equal to half of epsilon. So that means x is between these two values. And if x is between these two values, f of x, using the definition of f of x, 2x plus 1, is between these two values, etc. Given this epsilon, we use this delta. This delta forces this range of x, which forces this range of f of x, the dependent variable, etc. Now, if this isn't clear, just realize that not understanding the proof is something you can think about. But if you've gotten what we did before, you understand the definition of the limit. And that's all I was trying to do in this clip. So hopefully you've got that now. So I hope the clip was helpful. Thank you for watching. If you want this PowerPoint, you can find it here if you want to download it. And thank you.